Have you ever thought about like how much of science actually exists on scales that are just mind-bogglingly huge or tiny? Like we're talking billions of years of Earth's history, or the almost unimaginably small size of atoms, or the sheer vastness of space. It makes you wonder, like, why is it even important for us to like wrap our heads around these things that are so far removed from our everyday experience?
That's a really great question, and it actually gets to the heart of why understanding these extreme scales is so crucial. It's not just an abstract mental exercise, it's really fundamental to grasping the core principles of STEM fields, all of them. It provides the context for everything from like why your smartphone works to how stars are born. It
Yeah.
lets us see the big picture and the tiny details as part of this one universe.
Well, yeah, for sure. And that's exactly what we're diving deep into today, right? We've been looking at some research that explores how we, as humans, living our lives on this very human scale, can even begin to make sense of these truly extreme magnitudes. We're focusing on this one paper that lays out a framework for, how our brains tackle this, the mental tools we use, and even some surprisingly effective ways to kind of bridge that gap between our world and these vast scales.
And for anyone listening out there, it's totally natural if you're feeling a bit overwhelmed by the idea of billions of years or nanometers. That's exactly why we're here today. Our goal is to pull out the key insights from the research, pinpoint those moments of clarity that'll help you build a more intuitive understanding of these vast scales without getting lost in a sea of zeros.
Right, right. So the central puzzle we're tackling today is, how does our ability to see connections in relationships, how we reason, in other words, how does that help us build this mental bridge between our everyday understanding of the world and these crazy extremes of scientific scale?
Okay, so to start unpacking this, maybe we should first define what we even mean by relational reasoning, right?
Yeah. Yeah. What is that exactly?
At its core, it's our ability to recognize similarities and differences in the patterns that exist between things. These things could be physical objects, abstract ideas, or even complex situations. It's what allows us to see, for example, that even though a heart and a mechanical pump look totally different, they share a similar fundamental relationship. They both circulate a fluid.
Oh, I see. So it's about like looking beyond just the surface appearances and seeing that deeper structure.
Exactly. And this ability is absolutely fundamental to how we build our understanding of the world, by creating these conceptual categories. By recognizing these shared patterns, we can group things together, understand how they relate to each other, and make informed assumptions about them, right?
Okay. Yeah, I get that. So how does this then connect back to understanding these extreme scales that we're talking about?
Well, what's really fascinating is there's a growing body of evidence that suggests that our brains actually use a similar set of cognitive resources when we're trying to understand any kind of scale, whether it's the very short time it takes to microwave popcorn or the immensely long time span of cosmic evolution. Research across cognitive science, neurocognition, developmental psychology, and even studies comparing different species all kind of point to this shared cognitive toolkit.
So you're saying my brain isn't like totally rewiring itself when I go from thinking about like the length of my commute to the vastness of interstellar space.
It seems that way, and this information about magnitude, no matter what the scale, it seems to be stored in our minds as a combination of like specific metric information, the precise details, and then broader categorical information.
Can you give me an example?
Sure. Imagine remembering that some big event happened on, let's say, December 25th. That's the specific metric information, the date, right? But it immediately also tells you something more general, which is that it happened during winter. This way of using categorical information to anchor our understanding seems to be true even when we're dealing with the most extreme ends of a scale.
I see. I see. That's a really interesting way to think about it. So if our brains are using similar tools for different scales, does that mean we can use things we already understand to grasp the unfamiliar? That almost sounds like analogies, right?
You're exactly right. Analogical reasoning, which is a specific type of relational reasoning, becomes really important here. It involves finding those structural similarities, shared patterns of relationships between something that we know, well, we can call it the base concept, and something new and unfamiliar that would be the target concept.
So like saying that an atom with its nucleus and orbiting electrons is kind of similar to our solar system with the sun and orbiting planets.
Exactly. And the crucial thing about a good analogy isn't just about matching up features one to one, like the sun to the nucleus and planets to electrons, but about aligning the relationships between those features. So seeing that just as gravity keeps the planets in orbit around the sun, a similar force, though different in nature, holds electrons around the nucleus. It's the underlying structure of the relationship that we're mapping.
So that familiar base concept, it kind of gives us a framework to organize and visualize the new unfamiliar thing.
Precisely. When an analogy works well, the existing structure of that base concept gives us a way to organize the information about the target, makes it more visualizable, and that ultimately improves how well we understand it and even remember it.
This is fascinating. The research also mentions this idea that our brains are kind of recycling cognitive resources from how we handle small numbers to deal with these vast scales. Can you talk a bit more about that?
Sure. The idea is that instead of evolving completely new brain mechanisms for these incredibly large or small scales, we might be adapting or recycling those tools we already use for processing everyday numbers. So when you see a number like a billion, you might mentally break it down into smaller chunks, estimate within those smaller ranges, and then combine those estimations to get a sense of the overall magnitude.
Oh, so it's kind of like breaking down a huge project into smaller, more manageable tasks, right?
Exactly. And this ability to create and work with these complex units, seeing individual things as part of larger wholes, is something we see a lot in STEM experts when they reason about scale. They can seamlessly switch between individual components and thinking about them as part of larger groups. This unitizing seems to be a key characteristic of expertise in these fields.
Okay, so our brains try to find familiar patterns and structures to grasp these vast scales. But you also mentioned that the differences between scales are important. So where do things start to get tricky?
Right. So while there are similarities in how our brains approach scale, the same observation can mean completely different things depending on what scale we're looking at. For example, a few warm days don't necessarily tell us much about climate change, but if average temperatures are slightly higher over decades, that's a huge indicator of climate change. So the time scale provides that crucial context.
Meaning it's not just about bigger or smaller numbers, the meaning itself is tied to the scale we're looking at.
Absolutely. And it gets even more complicated because the properties of things can change as we move across scales. A classic example is what Galileo observed centuries ago about falling objects. A horse falling from, say, 8 feet is likely to break a leg, but a dog falling the same distance will probably be just fine. That's because the relationship between surface area and volume changes as things get bigger, and this has huge implications in areas like engineering and construction. What works at one scale simply won't work at another.
That's a really good illustration of how scale isn't just about numbers, it's about how things actually work differently.
Yeah, and even how we conceptualize different scales can be different. Our experience of time is based on, durations, seconds, minutes, hours. But geologic time is organized around major events like the age of dinosaurs or the rise of mammals. These aren't neat, evenly spaced durations. They're defined by big changes in Earth's history.
So we shift from a kind of continuous measured scale to one based on these big irregular events.
Exactly, and that's where actively reasoning about the differences becomes important. Researchers have identified a few ways we do this. One is anomalous reasoning, which is basically recognizing when something deviates from a pattern or expectation.
So like noticing a spike in global temperatures in an otherwise stable climate record.
Exactly. Then there's antithetical reasoning, which is about identifying opposites like hot versus cold, large versus small. And finally, there's antinomic reasoning, which is recognizing incompatible ideas, things that can't logically exist together. Like, imagine something being infinitely large but also contained in a finite space. Those are incompatible ideas.
I see. How does thinking about these differences help us understand new scales?
Well, reasoning about differences can actually drive conceptual change. When we try to apply a familiar concept to a new scale and it doesn't quite fit, we're forced to reevaluate and even completely rethink our understanding.
You mentioned fractions earlier. How do they illustrate this idea of differences leading to new understanding?
Fractions are a great example because they often represent the first time students encounter numbers that don't behave like the whole numbers they're used to. The idea that multiplying always makes things bigger is simply not true with fractions less than 1. So learning about fractions forces them to rethink their understanding of numbers.
It's about realizing that numbers are more than just a simple, uniform line of whole units.
Exactly. And Antithetical reasoning, thinking about opposites, is really helpful here. It lets us visualize relative magnitudes. We can position those opposites as the ends of a kind of mental continuum. This helps us grasp where something fits, even if the absolute magnitude is way beyond our experience.
This idea of a mental number line, can you elaborate on that a bit?
Yeah. Research suggests we internally represent numbers along a mental line, usually from left to right, with smaller numbers on the left and larger on the right. Having a clear and accurate mental number line seems to be really important for math reasoning and understanding numerical relationships.
And how does this develop in our minds?
Well, kids often start with a compressed number line, where smaller numbers take up more space mentally and larger numbers are squeezed together at the higher end. As they learn more, this becomes more linear and evenly spaced. But some people might still struggle with representing really extreme scales accurately, which can affect how well they reason about those magnitudes.
So even our basic way of thinking about numbers can be a barrier when we're dealing with these extreme values.
Yes, and this leads us to thinking about those barriers to relational reasoning about scale. It's not always a smooth process, and analogies, while useful, can sometimes fail us.
You're saying these mental shortcuts aren't always reliable when it comes to these huge differences in scale?
Right. Relational reasoning and analogies are great tools, but they have limits. They can fail to create genuine understanding and even lead to misconceptions, which can be hard to change.
So what are some reasons these approaches can fall short with extreme scales?
One big barrier is not having a really strong base concept to start with. If we don't understand the thing we're comparing to very well, it's hard to make meaningful connections to the unfamiliar target. And even if we do understand the concept, we might not have a solid, linear sense of its magnitude. Like, we might know the Empire State Building is taller than a house, but we probably don't have a precise, intuitive grasp of how much taller as a ratio.
So the base of our analogy needs to be something we not only understand conceptually, but also in terms of its actual magnitude.
Exactly. Another problem is when there are too many differences between the base and the target. This can lead to irrelevant alignments where we focus on surface similarities that don't reflect the underlying structure that's actually important. This is especially true when those irrelevant features are more noticeable or salient to us.
You mentioned the analogy of comparing geologic time to a 24-hour clock, which is a really common one. What are some issues with that?
That's a great example. While both a clock and geologic time represent time passing, the key difference is how they're divided. A clock has equal divisions, every minute is the same, every hour is the same. But geologic time is divided based on major events, and these divisions are vastly different in length. So someone using the clock analogy might wrongly assume that the periods of Earth history are roughly equal, which is not true at all. They're focusing on the equal slices of the clock, not the actual huge differences in time they represent.
Yeah, the visual of the clock can be misleading when you apply it to the very uneven spans of geologic time.
Exactly. And we can also have psychological barriers based on our pre-existing understanding of space or function. Like, if you're imagining the solar system using a road trip analogy, your knowledge of driving distances might distort your understanding of the astronomical distances involved. Then there are practical constraints, like trying to represent geologic time on a roll of toilet paper in a classroom. The physical model itself can limit how accurately the scale is represented.
So just presenting an analogy isn't enough. We need to be careful about how we construct them and how we help learners use them effectively.
That's right. And this brings us to, how can we help people develop a better understanding of these scales? Are there teaching activities that research has shown to be effective?
The research mentions progressive alignment. What is that?
It's a strategy that recognizes the big gap between human scale experiences and these extreme scientific scales. Instead of trying to jump that gap in one go, you build understanding step by step. Learners start by aligning things that are already somewhat similar. This helps them see the important relationships, and then they can gradually extend that to more unfamiliar and extreme concepts.
Like building a staircase instead of trying to leap across a canyon.
Perfect analogy. And there's also hierarchical alignment. This involves mapping increasingly larger scales onto the same amount of physical space while making sure everything stays aligned. The key is that at each step, learners actively figure out where all the previous scales fit within this new, larger scale. This process of nesting scales within each other using the same space really highlights those magnitude differences in a clear and visual way.
Can you give an example of how this works?
There's this great activity for teaching geologic time where you use a fixed length, like a meter stick. Students start by making a timeline of their own life on that meter stick. Then they make a timeline for an average human lifespan on that same meter stick, figuring out where their own life fits within it. They keep doing this, adding the history of their country, then human history, then human evolution, all the way up to the entire geologic timescale, always on that same meter stick. At each step, they calculate how many years each centimeter represents and where the previous timelines fit. This really helps them grasp those vast time spans.
Wow, by keeping the space the same, the shrinking of time as you go bigger must be really obvious.
Exactly. Another effective activity is corrective feedback. Here, learners predict where something falls on a scale and then get immediate feedback on whether they're right or wrong.
Why is that immediate feedback so important?
It helps learners identify and correct any misconceptions they have right away. And if they do this multiple times with some time between sessions, that's called spaced practice, it really reinforces the learning.
How is this used to teach geologic time?
In one study, students were shown the regular geologic timescale, which is often nonlinear, next to a blank linear timeline of the same length. They had to predict where specific events would fall on that linear timeline using clickers. Right after they answered, they'd see the correct answer, with lines connecting the event on both timelines.
So they actively engaged with the linear scale and got immediate confirmation or correction.
Yes. And what's interesting is that just seeing the aligned timelines without making a prediction first didn't really help. In fact, it sometimes even made their test scores worse. This tells us that the act of predicting is what makes them really think about the scale and try to map it linearly.
So if they don't actively think about it, just seeing different representations might be confusing.
Right. And the study found that doing this activity led to better test scores in a geology course, probably because understanding geologic time gave them a better context for other concepts.
These are really interesting strategies. The research also talks about the importance of a unified scale curriculum across STEM subjects. Why is that?
The idea is that scale isn't just about one subject, it's fundamental to all of STEM. A unified approach means students learn about scale in a consistent way across biology, physics, chemistry, astronomy, everything. This helps them build a stronger foundation for understanding all these different fields.
So instead of teaching scale separately in each subject, we should be connecting them and using the same methods across the board.
Exactly. By using consistent techniques based on relational reasoning, like the alignment strategies we discussed, students develop a flexible understanding of scale that they can apply anywhere from tiny cells to huge galaxies.
What would this unified scale curriculum look like?
It would emphasize giving students lots of chances to practice aligning scales, using spatial representations, and getting immediate feedback. It would involve them actively predicting things about scale, using space practice to reinforce learning. And it would strategically use activities like the hierarchical alignment and corrective feedback ones we talked about to help them bridge those big gaps between human scales and the extreme scales we find in science. These activities can be adapted to teach about any scale, not just geologic time.
This has been a really eye-opening look at how we deal with extreme scales. So to wrap up, what's the main takeaway from our conversation?
The biggest takeaway is that our ability to reason relationally, to see patterns in relationships, is absolutely essential for understanding these huge and tiny scales that are outside our everyday experience. We do this by connecting these extreme scales to things we're familiar with, but also by carefully thinking about the key differences between them.
And it seems like the specific learning activities we use can make a huge difference.
Absolutely. Activities that make people actively align different scales, especially using visuals and immediate feedback, are really effective at building a better understanding of these challenging magnitudes.
This makes you think about how often we encounter huge or tiny numbers in everyday life, in the news, at work, even just out of curiosity. So here's something to think about. Now that you know more about how we reason about scale, how might you approach information with really big or small numbers? Maybe you'll start looking for those underlying patterns, try visualizing the information, or break it down into smaller pieces.
That's a great question to leave our listeners with. And remember, learning to think about scale is an ongoing process. Keep those strategies in mind, looking for analogies, thinking about the differences between scales, and practicing aligning different representations. Those can help you understand other challenging concepts you might encounter in the future.
Thanks for listening, everyone.
And until next time.